Ah, welcome to the third video in our series on free body diagrams and forces and all this great stuff. If you have not fully watched the other two videos, please make sure that you watch them in their entirety before watching this one. This one is going to assume that you learned the things that were in there, so please also don't feel like it might be a good idea. Please feel like it would be a good idea to pause this video and go reference the other ones if you ever get confused as to what's happening here. Today, what we're going to do is go over types of friction, and they are either static or kinetic. Up until now, we just kind of said friction is friction. It's a force that opposes motion. All of that is true, but that is an oversimplified way of thinking about it. Friction is indeed a force that opposes motion. So you can go ahead and see in this little sample free body diagram that the pushing force is going here, the friction is going here, they're opposite, they are working against each other, and that's what we learned last week. An example of course, rubbing your hands together is indeed a way of friction, a way to experience friction. You experience the friction between your hands as the heat that is produced. Okay, so there are some things that we already know. We know that the force of gravity, Fg, equals mg, mass times gravity. We already know that. So if I look at this box on the right and it says 10 kg, and I want to say, well, let's draw all the forces. There are things here that we already know. I expect you to know that the down arrow would be mass times gravity, or in this case, 98 newtons. I expect you to know that at this point. We also know that the normal force must cancel. God, that was a straight line. That's awesome. Must cancel the F of G. So if this is the F of G going down, okay, this is the F of N going up. And they must cancel. So if there was 98 down, it was 98 up. Now, for those of you who did all the work last week, you may have seen some comments. Please do not forget the up and down arrows. They will be important. And today is the day where we're really going to see why they matter. Nevertheless, if I look at this box of 10 kilograms, we know that the down arrow is just going to be mass times gravity. We know the up arrow's got to be the same thing to cancel it out. And every single time, the friction and the push, at least one of them had been given, and we could solve for the other one. Or maybe both were given. But we've never had to calculate the friction straight from other forces before. What do you mean by that? Let me show you. The friction has always just been given, hey, the friction is 5 newtons. The friction is some amount. But that's not really always going to be the case. The friction is actually going to be calculated from an equation. So instead of saying the friction is 5 newtons, we can now use the equation right here to mathematically calculate what the friction is going to be. Force of friction equals mu times the normal force. Now, this is called mu. It's a Greek letter mu. And what it represents is the coefficient of friction. What is that? We're going to get into that in just a sec. But the force of friction is always going to equal the coefficient of friction times the normal force. So we have these three things together. This is the equation for friction. Now, what is the coefficient of friction? Let's talk about what it is. So, friction exists every single time objects touch. But objects could touch in different ways. Objects can go ahead and be still or at rest. And if objects are at still or at rest, then they are experiencing what's known as static friction. Static friction occurs when things are still. So if you think about literature, if you've ever heard of a static character in literature, a static character is a character that does not change throughout the course of the story. Static means staying still. So if you have these two objects, so if you have a box on the floor like we have, it looks like it's flat. But if you really zoom in at the microscopic atomic level, the surfaces, no matter how smooth they may seem or feel to your hand or to your eye, at a microscopic atomic level, this is actually what it looks like. There's all these jagged edges of atoms kind of jumping up, and they kind of grab onto each other. What the coefficient of friction does is it measures how much these surfaces attract each other. That's it. So every object and every surface will have a different coefficient of friction. So the coefficient of friction of ice, as you can imagine, would be lower than the coefficient of friction on sandpaper. So I don't want us to get too lost in the weeds here, but this is what I want you to know. I want you to know that when two objects are touching each other, like your computer sitting on your desk or a book sitting on the floor, they are touching each other. The book and the floor are touching each other. The computer and your desk are touching each other. There is this static friction interaction that is causing them to stay together. You know this because if you push your computer in front of you ever so slightly, your computer doesn't move. Why? Because the static friction resists that push. You have not given it enough force to actually accelerate it because of all these jagged edges, these microscopic jagged edges that are connecting between the two surfaces. Static friction is the friction that occurs when an object is at rest. So, static friction is used to determine if an object moves from a push. What do you mean by that? It is possible to push something and not have it move. You could go out and if you have a couch somewhere and you could give that a push, you may not be able to move it unless you give it a really hard push. And some people may not be able to move it even with a hard push. That doesn't mean you're not pushing it. Newton's laws say if you push something, it should go. So let's go ahead and see how static friction plays a role. So let's assume that we have this crate that is pushed to the right 15 newtons. So we have our 10 kilogram crate. And if we know that even though it doesn't say gravity is acting on it, we know that we're on planet Earth and gravity is acting on it. So we have our down arrow of 98 newtons. We have our up arrow, our normal force, of 98 newtons. Okay? We have our push 15 newtons. Oh, that was a straight line. We have our push 15 newtons. Oh, doing good, Vizito. Push to the right of 15 newtons. So here's what we can do. Now we can mathematically calculate what the friction is on this object. Wait, Bizzuto, I don't know how to do that. That's okay. If you don't remember, and I don't know if you guys are taking notes on these videos or not, but I'd recommend maybe jotting a note down or two is not a bad idea. I said that the force of friction equals the coefficient of friction times the normal force. The coefficient of friction, the coefficient of static friction, in this case, mu sub s. The s means static, the mu means coefficient of friction. In this case, it has a coefficient of static friction of 0.20. The coefficient of static friction has no unit. It is a unitless quantity. It's odd. We don't have a lot of these in physics, but here's our first one. Coefficients tend not to have units. This quantity right here in the equation has no unit. It's just a coefficient, no unit. Okay. So what we are going to do is this. We are looking for the friction in this problem. The friction is what we are looking for. We know what the coefficient of static friction is. It's 0.20. 0.20. We know what the normal force is. The normal force is this 98 because it has to cancel out the gravity. So this is what I'm going to do. I'm going to type 0.20 times 98 in my calculator, and I'm going to get the force of friction equals 19.6 newtons. So I want to just think about this conceptually. Let's just think about this. So what I'm saying is that this is 19.6. So if the push is 15, but the friction is 19.6, is this moving? What does your gut say? This is the key. If the external push is bigger than the static friction, then the object moves and accelerates. So if the force of the push, the external push, the applied push, is greater than the force of static friction, then it moves. And if it moves, then the acceleration is not 0, it's some other number. We can calculate it. However, if the push is less than or equal to the static friction, then it does not move. That means the acceleration is 0. This is a critical slide. I need you guys to take some time and think about it. If you push something and you don't push it more than the friction, it doesn't move. If your push is greater than the friction, it does move. This is kind of logical if you think about it, but if you just are trying to memorize equations and formulas, take the time and think about this. If the push is more than the friction, it moves. That makes sense. If the friction is more than the push, it doesn't move. Friction resists motion. So in order to have motion, the push must be bigger than the friction. So let's see how this plays out. So let's look at this 15 kilogram box sitting on the floor. If it has a mu sub s, a coefficient of static friction of 0.3, will it move if it is pushed to the right with a force of, okay, and then there's 4 forces here. Okay, so I don't really know what to do, but let's start by drawing some arrows. I know that gravity pulls down on this. Mass times 9.8 is going to be 147 going down. If I have 147 going down, that means I have to have 147 going up. So here's the question. I know that there's going to be, the push is going to be over here. It says push to the right. So here's your F of P, your external push. I know the friction is going to go this way. All right. Well, what is the friction? What is the static friction? Well, the coefficient of static friction is 0.3. The normal force is 147. So what is the force of friction? The force of friction is the following: 0.3 times 147. And if I did this correctly, we know that the force of friction is 44.1. Okay, so there's the friction. So now we know what the friction is. We see the push on the other side. If the push is bigger than the friction, it moves. So if the F of P is 44.0, will it move? Well, is 44.0 bigger than 44.1? No. Then will it move? No. It will not move. What if the force of the push is exactly 44.1? If the force is exactly equal, the friction keeps it still and it doesn't move. In order for it to move, the push must be greater than the friction. So does 44.1 move it? No. But what if it's just 44.2? What if it's just a little bit more than the friction? If ever the push is bigger than the friction, it moves. That means, does 44.2 move it? Yes. Does 44.3 move it? Yes. Does any number bigger than 44.1 move it? Yes. So what we have done here is we calculated the static friction and we compared it to the pushes, and we were able to determine in each situation if it moves or doesn't move. So static friction is the friction that occurs when objects are still touching each other. But once you push something, let's just say you're talking about that heavy couch in your room. If you push something, here's a question. Have you ever noticed that if you push something, it takes a lot of force to get it moving, but you don't have to push quite as hard to keep it moving if you're just pushing it along the floor? We're not talking about lifting, we're just pushing and sliding something. You may see sometimes, like in movies, or cartoons, they'll exaggerate it. If you push something, they're pushing really hard, and then it slides out from them, and it slides forward, and the person falls down. I don't know if you've ever seen something like that, but try it. You can even try it with things in front of you, your computer sitting on your desk. You push it. It doesn't take a lot of force. It doesn't take as much force to keep it moving as it does to get it moving. So once an object starts moving, what happens is a different form of friction takes place. When you had static friction, when two objects were still, not moving, not changing, kinetic friction, I look at the word kinetic, like kinematic, and this has to do with moving. So moving friction, kinetic friction, this is the friction that occurs when objects are sliding across each other or moving across each other. Kinetic friction is always lower than static friction. So if you think about it, if you think about that picture we looked at before of all those jagged edges, if an object is sliding across something, it doesn't have time to kind of fall into those cracks and crevices. It just keeps moving. So therefore, there's less friction, there's less contact to exist, and less force to slow it down. So once an object starts moving, kinetic friction kicks in. So static friction just determines if it moves. Kinetic friction will go into the free body diagram once it starts moving. And kinetic friction is always less than static friction. It always takes more of a push to get something going than to keep it going. And all friction uses the same equation. So we're not actually using a different equation. We're still going to use this same equation. So let's take a look at some questions like this. Okay. A 20 kilogram box is pushed to the right at 15 newtons. Oh my, I have made a mistake. I apologize. 20. Good. Oops. 20. You'll see what's coming up. 15 is clearly coming up. All right. A 20 kilogram box is pushed to the right at 50 newtons. Okay, so what I'm going to do is I'm going to draw two free body diagrams. The one on the left is going to have the static friction. The one on the right is going to have the kinetic friction. And I'm going to show you why we're going to have two in just a second. So static, kinetic. So the coefficient of static friction is 0.2 and the coefficient of kinetic friction is 0.1. What is the box's acceleration? Well, let's think about this for just a second. Let's go ahead and get the gravity. We know that gravity is going to be 20 times 9.8, or 196. If that's 196 going down, we know it's going to be 196 going up. Okay, so far so good. And it says it's pushed to the right at 50 newtons. It's pushed to the right at 50 newtons. Okay. So here's the first question we have to ask ourselves. Does it move? Well, in order for it to move, the push must be bigger than the force of static friction. So how do we get the force of static friction? We get the force of friction is going to equal mu F of n. So the static friction is 0.2. The force, the normal force is 196. And I just multiply those together. What is 0.2 times 196? I hope you're doing this together and you'll realize that that's 39.2. So here's the question. Is the push bigger than the friction? Is the push bigger than the friction? Yes, it moves because the push is bigger than the friction. It moves because the push is bigger than the friction. So once it starts moving, static friction goes away. And what happens is now kinetic friction kicks in. So it says, what is the box's acceleration? So once it starts moving, it's now accelerating. So now, because it's accelerating, we're not going to use static friction anymore. We just have to figure out if it moved. Now what we're going to do is we're going to use the kinetic friction. So everything is going to stay the same. The push is still 50. Gravity is still 196. Normal force is still 196. But the only difference is that instead of the static friction, instead of the coefficient of static friction, we're now going to use the coefficient of kinetic friction. Once it moves, you're going to go ahead and use the coefficient of kinetic friction in the equation. So let's see how this works out. So force friction equals 0.1 times 196. And what does that equal? If you have your calculators out, I trust that you could do that. That means that the friction here is 19.6. So you just use the static friction to determine if it moves. The kinetic friction is what you're going to use in the free body diagram and get the acceleration. So I say, what is the box's acceleration? Well, we just had problems like this all last week. To get the net force is 50 minus 19.6, 30.4. We just subtract the push and the friction, just like we've been doing. The mass is still 20. That hasn't changed. The acceleration is indeed 1.52 meters per second squared to the right. So, lots of steps. First, use the static friction to determine if it moves. If it moves, then you use the kinetic friction in the free body diagram, get the net force and the acceleration. Bizzuto, I need to see you do more practice problems. Agreed. Okay, here we go. What is the acceleration of a 25 kilogram crate that is pushed right 45 newtons when the coefficient of static friction is 0.25 and the coefficient of kinetic friction is 0.15? Okay, don't really understand what to do yet, but I have my two boxes, static and kinetic. All right. Let's go ahead and see how this is going to work. Let's do this together. Take out your calculators and type 25 times 9.8. You'll go ahead and write that number as the down arrow, whatever number that is. It happens to be 245. So 245 going down, 245 going up. $245 going down, $245 going up. It's pushed right 45. Oh, nice. Okay. So let's figure out if it moves. So we are going to use the friction equation. The force of friction equals 0.25, all right, times 245, the normal force, 245, the normal force. So when I do 0.25 times 245, I get 61.25. Okay. So that means this arrow is going to say 61.25. Okay. Wait a minute. Does it move? Is the push bigger than the friction? The push is not bigger than the friction. Does not move. It does not move. That means we can't even draw this because it's not moving. So this is why you have to do it step by step. You always have to go ahead and do the static friction first. And then the whole point of doing the static friction is to determine if it moves. In this case, we found out that it doesn't move. And if it doesn't move, what's the acceleration of an object that is not moving? 0. If it doesn't move, it's not accelerating. Only if it did move, would we do the kinetic diagram. In this case, because it's already not moving, we don't have to do the friction of it if it was moving because it's not moving. So static first, then kinetic. Ooh, look at this one. This one looks good. Okay, so what is the acceleration of a 17 kilogram crate? All right, so I'm going to write static right here. I wonder if we'll even need the kinetic this time. So just so you know, I've taught this many, many years, and I've often had students just always jump to the kinetic because they feel like doing the static's a waste of time, and they get the acceleration with the kinetic. And chances are you might be able to do that. But if the crate never moved, then what you're solving for is erroneous. It's irrelevant. It doesn't happen. It doesn't matter how fast we'd be going if it's not moving. So let's go ahead. Let's do the static first. 17 times 9.8 is indeed 166.6. There it is. Down, up. 166.6. Awesome. Okay, it's pushed to the right 58 newtons. Nice, Pizzuto. 58 newtons. So it's pushed to the right 58 newtons. Let's go ahead and see what the friction is, what the static friction is. So the force of friction equals 0.18 times 166.6. All right, so let's type that in. 0.18 times 166.6 is, I'm getting about 29.98. I'll say 988. Sure, I'll just say that. So, does it move? Is the push bigger than the friction? It moves. Now that we know it moves, now we can go ahead and do a kinetic friction because the push is bigger than the friction. It moves. So now, but when you do the second one, think about it. The down is still 166.6. The up is still 166.6. The push is still 58, but the only difference is this friction. Instead of using static friction, now we're going to use kinetic friction. So we're going to do the force of friction is going to be the mu F of n. So the force of friction would be 0.09 times 166.6. Sorry, my hand. Sorry, I need to get that together. All right, 0.09 times 166.6. So I'm getting 14.994. Awesome. So I'm getting that the friction here is 14.994. So what I'm saying is this. We figured out that it moved because the push was bigger than the static friction. Then we figured out the kinetic friction and put it into the free body diagram right here. Now I'm going to get the net force the way I did last week when I did the push, the x vectors, and I'm getting a net force of 43. I'm just going to call 43. I know it's not. Just, we're rounding. The mass is 17. So that means the acceleration is going to be 43 divided by 17 is about like 2.5 something. And I know there's more decimals, but there it is. To the right. Thoughts, problems, questions, concerns. Thoughts, comments, questions, concerns. So this is what you need to know. I know I started the beginning of this video a little abstractly. If you didn't understand why the friction is different between static and kinetic, I'm going to be honest. That's not the biggest point. This is what I need you to know. This is what I expect you to understand from this presentation. I need you to know there's two types of friction that act on objects. Static friction is when the object is at rest. Kinetic friction is when the object is moving, sliding across the surface. So think about the couch still and then pushing the couch across the room. One is static friction, one is kinetic friction. I need you to know that the friction equation is the same for both types of friction. This is the generic equation. The force of friction equals the coefficient friction times the normal force. I need you to know that every single time you use this equation, you can make sure that you are using static to determine if it moves and kinetic to know what goes in the free body diagram if it moves. By the way, I will always have to give you the static and kinetic frictions of surfaces. This is not something that I just expect you to know. That will always be given information. When solving, you must first determine if an object is moving by using the static friction and compared to the external push. I have been trying to really hammer home this point. This is the point that students really get confused about. You have to determine if it moves using static friction. And if the push is bigger than the static friction, it moves. And then once the object is moving, only if the object is moving, if you will then use the kinetic friction and put it into the free body diagram and solve like we did last week. So you may not use the kinetic friction all the problems. You will always solve for the static friction. If you find out that it doesn't move, your acceleration is 0. Only if it moves will you use the kinetic friction. So, questions, thoughts, comments, concerns, please email me. This is a video on how to go ahead and solve for static and kinetic friction and putting them into a free body diagram. A lot of people commented that they want to get more immediate feedback on how to do problems. So I essentially taught the lesson that was in the Khan Academy that was assigned to do tomorrow night. It's 4 questions. All the questions are exactly like what we just went through in this presentation. If this presentation didn't work for you, feel free to watch the Khan Academy videos, but the only thing that is graded is to do those 4 Khan Academies. Please let me know if you need any help, email me with questions, and I am here to assist you as needed. Good luck.